Yeah, if you were to take a, say you have iron liquid down here, and up here you have a liquid slag, say it contains alumina, SiO2, and CaO, and up here you have oxygen gas. Now the oxygen gas should react with the iron to form iron oxide in the slag. So we can talk about iron plus oxygen forms FeO, which dissolves in the slag. Okay, but if you just set this thing up this way, you'll find there's no direct contact now between the oxygen and the iron. The reaction has to occur by diffusion. Now the slag is an ionic material. The slag contains oxygen ions, and it contains oxygen ions, silica, calcium ions. It's an ionic conductor. The neutral oxygen, either as an atom or as a molecule, is extremely insoluble in here. So the oxygen cannot diffuse across the slag to the iron as the forms of a molecule. It would have to become an ion. But to become an ion, it needs electrons. Where's it going to get the electrons from? Similarly, the iron cannot diffuse through the slag as an iron atom. It has to diffuse through the slag as an ion, and it needs to lose electrons somewhere. So if you do it this way, if you set this thing up, you'll find an extremely slow reaction. But now if you were then to take and make an external electrical contact, so let's say you put a metal grid, platinum screen on the surface, for example, and you connect that up through an external circuit here where electrons can move. Now you suddenly find the reaction becomes very rapid. An oxygen atom lands on the surface, picks up 2 electrons, becomes an ion, and diffuses through very fast. Or an iron atom loses 2 electrons to the external circuit, becomes an iron atom, and moves an iron ion, and moves very quickly through the slag. So the minute you put an external circuit here, you'll find the reaction, the formation of FeO is very, very fast, okay, indicating the ionic nature of the slag. This harkens back to a classic experiment in 1941 or 2 by Carl Wagner, showing the ionic nature of, he had silver bromide, and oxygen, and bromine. It was the same thing. Close the switch, silver bromide layer grows very fast. Open the switch, silver bromide layer stops growing. Okay. Now, in the slag, however, suppose you now then replace your external circuit. There's no external circuit, but what we do is we start off with a little bit of iron in the slag. We start off with the slag. For the example I just gave you, I said the slag was alumina, calcium, silica, completely ionic. We put a little bit of iron in here to start with, 1 or 2%. Now we have iron 2+, and we have iron 3+, which now the slag now becomes a partial electronic conductor. Electrons can move through the slag by hopping from 2+ to 3+. Okay, so now you don't need an external circuit because the slag itself is your electronic conductor. Okay, so the oxygen atoms land on the surface, pick up 2 electrons, which would move through the slag, and now they become oxygen ions, which can diffuse down. Same thing with the iron. It loses 2 electrons into the slag, and it loses an iron ion up through the slag. Okay, so if you take your slag with no reducible species, no species that have 2 oxidation states in the slag, your reaction will be very slow unless you have an external circuit. But the minute you put in something like iron or chrome or manganese, then the slag is an ionic conductor, electronic conductor, and the thing goes much faster. Okay, because the electrons or positive charge will move one way or the other through the slag. I also once, a long time ago, did an experiment. Back when I did experiments, the idea was the rate of reaction of a sulfur-containing slag with the atmosphere. Practically, you take a slags contain sulfur, you put them out in the atmosphere in the yard of the steel plant to cool down. The sulfur reacts with the oxygen in the air, and you get a lot of SO2 coming off, pollution. So here we had a slag, and the slag contains sulfur ions. You reacted with oxygen. The reaction should be oxygen plus sulfur ions form oxygen ions. Oxygen plus 2 sulfur ions form oxygen ions plus, well, that's 2 gas plus 2 oxygen, SO2 or something else. Balance it out, something like that. You get a balance anyway. The point is the oxygen ion has to react with the sulfur ions to form oxygen ions and SO2. Okay. When I did this with a slag alumina, but so not just as a reaction, but there's a charge transfer. You got oxygen on the surface here, but the oxygen has to gain 2 electrons. There has to be a charge transfer between the oxygen and the sulfur. If you just had a slag, calcium-aluminosilica, an ionic conductor, the reaction went on, but it was quite slow. But if I put a small amount of iron in here, as soon as I added a pinch of iron, just a little bit of iron, then now this is an electronic conductor, so now at the surface the oxygen ions can form oxygen ions very rapidly with an exchange of electrons through the slag. So the charge transfer part of the whole reaction, which was a slow step, and the mechanism became very fast. Add 1% of iron and the reaction was 100 times faster. Okay, because of the electronic nature of the slag. So these things can be quite important in okay, there are several steps. When you do the step, there's several steps in a reaction, but it seems that the charge transfer step was the slowest. Somehow the neutral oxygen forming an ion, or the ionic sulfur forming a neutral atom was the slowest step in the reaction mechanism. Okay, because the only way to get electron transfer if you didn't have the iron there would be for the oxygens and the sulfurs to actually somehow come in contact with each other and transfer their electrons. I don't know the details, but I certainly know when I added just a pinch of iron to make it an electronic conductor, it was far, far faster. And I did this as a function of the rate as a function. This was a totally different thing. I did it as the rate as a function of oxygen pressure. And as I increased the oxygen pressure, as you would expect, the reaction got faster. To a point where suddenly I increased the oxygen pressure beyond about 1/10 of an atmosphere, and suddenly the reaction slowed right down. Way down. To my surprise. Why would that be? And it was reversible. Went back to a lower oxygen pressure, and the reaction rate goes up. The reaction rate goes up with oxygen pressure to a point and then drops off very rapidly. Because you're forming sulfate. Rather than forming SO2, I was forming SO4, which stayed in the slag as sulfate ions. Okay, so the solution to that was, if you wanted to, I don't know whether anybody implemented it, but if you wanted your SO2, you're putting the slags out in the atmosphere. And you want, while they're cooling down, they're forming a lot of polluting SO2. You want to stop that as far as possible for a while until the thing cools down. Okay, the way to do it is not to lower the oxygen pressure, but to increase the oxygen pressure. As long as you keep the oxygen pressure quite high, blow air. The oxygen pressure was about 0.1 atmosphere, so blowing air, I mean, if the air got depleted at the surface, the oxygen pressure is 0.21, so that's enough to form the sulfate. But if there's a reaction going on and the oxygen becomes depleted at the surface, if there's a reaction, then you're going to speed it up. So just keep your air flowing over the surface, and that'll slow down the SO2 production. It seems kind of counterintuitive. Anyway, this electronic nature of ionic materials. And that applies to the solid and the liquid ionic salts. Okay, on the same vein of the last thing here that I want to talk about, again it's a bit of an aside, so why do I keep losing it? I think we'll go to the homework problems again, and I'm going to go to number 17, 18. Alright, here's 1718. Point defects in silver bromide. That's one to do. Alright. Point defects in silver bromide. Alright, in silver bromide, solid silver bromide, the principal defects are silver interstitials. So a silver, if you can't read that, a silver interstitial is AgI. See, this was written up wrong. It shouldn't be that way. Somebody wrote that wrong. It should be silver interstitials are this way. And cationic vacancies on the silver lattice. So this is cationic vacancies on the silver lattice. They'll have a negative net charge. Interstitial silver ions will have a net positive charge on what's normally on the interstitial side. The concentrations of these defects are related by simple equilibrium. Okay, remember you're forming defects. Remember when we did the compound energy formalism. Here you have silver bromide. Here you'll have the steps. Here you end up with the concentrations of the two defects, and you always end up with xy over 1 minus x times 1 minus y is exponent of something minus delta G1. Okay, you always end up with something very close to this. The product of this defect times the concentration of this defect divided by the concentrations of the defect-free sites is equal to the exponent of some sort of an energy term for forming the defects. This is approximately constant. The denominators here are approximately 1. So basically, if you're in dilute solution, all of these things end up with very simple that the product of the concentrations of the two defects is a constant, which depends upon the energy of forming the defect. Okay, this might be x squared y if there's two spaces or something like that. Okay, so all of these things reduce down to the simplest equation that the product of the concentrations of the two majority defects is approximately constant to a first approximation. If you want to do it more. This is the main point of, this is the main terms in the equation. You have the other terms, but they're secondary. Basically, the product of this 1 point defect goes up, the other point defect concentration goes down. They're dilute solutions, so, okay, and this from xy over approximately 1, x and y are small, so the denominator is 1. X times y is a constant, which is exponential of the formation of the defects over RT. This isn't exactly true, but it's close to being true. Okay. Okay, so it simply means that the product of the concentration, so we'll do it this way, the concentration of interstitial silver ions times the concentration of vacancies is approximately equal to constant. So the concentration of your interstitials times the concentration of your silver ion vacancies is approximately constant. You can look at this too as simply a formation reaction. You would have silver bromide. Well, let's do it this way. This is silver on the silver sites and bromine on the bromine sites. Okay, form silver interstitial site. Well, silver on the silver site forms a silver interstitial plus a vacancy on the silver site. So this is basically in the lattice. You simply imagine that you have a silver here, where silver goes to form a silver interstitial, leaving a vacancy here. So there's a equilibrium constant. You form a vacancy. They can recombine as well. The silver ion and the vacancy move around the crystal. The silver ion can move around, comes back to the vacancy, it falls back into the vacancy and reconstitutes the silver. And the reaction goes back the other way. That would be an annihilation. Okay, so you have two rates. You have the forward rate, which is thermally activated silver. The silver is bumping around. Every now and then a silver pops off its lattice site, goes into the interstitial, leaving behind a vacancy. Okay, as you increase the temperature, this is a thermally activated process. Okay, the higher you go in temperature, the greater the probability is of a silver popping into the interstitial lattice. And you also have now, you have the recombination. These things move around and there's a certain probability they're going to come back together. The probability of these two things meeting is in fact x equal to this. Anyway, this is the way you write it. Now, this is the interesting thing then. The two defects can act as charge carriers. This acts as a positive charge carrier, electrons. If you put your silver bromide crystal between two electrons, you'll find that electrons can move through it as vacancies, and you find that holes, positive holes, move the other way as silver ions. It's an electronic conductor. The conductivity depends upon the product. There's conductivity by silver ions, there's conductivity by vacancies. But the silver ions have a net, interstitial silver has a net positive charge, these vacancies have a net negative charge. So this is electronic conduction. There's no movement of the ions, there's just movement of electrons in the hole. No, sorry, what? Start all over again, forget what I said, pretend I'm not here. This is ionic conduction. The silver ions is an ionic. It's an ionic conduction. This is ionic conduction. The silver ions move, not as electrons, they hop as ions. Positive ions. The vacancies also have a hopping mechanism. You have a vacancy here, the silver is next to it, the silver hops into the vacancy, now the vacancy is here. Okay, so it's definitely an ionic conduction. Alright, it's ionic conduction. You can have ionic conduction of silver in one direction, you have ionic conduction of vacancies in the other direction. Both of them are actually. If vacancies go this way, it's equivalent to silver moving this way. Okay, so this is an ionic conduction. Alright. When you make small additions, so we take here pure silver bromide and it has a certain conductivity. As we add cadmium bromide into the solid solution, dilute solutions, at first the conductivity drops and then the conductivity goes back up again. This is ionic conductivity. Explain why this should be the case. Okay, what's going on? This is a solid, remember? So, the point is there's two kinds of conduction. There's a conduction by the silver interstitials and conduction by the vacancy. The conduction depends on two things. It depends on the concentration of the charge carrier, and it also depends on its mobility, how easy it is for it to hop. The silver ions have to hop from one interstitial site to another. They got to kind of move themselves through the interstitial lattice. The vacancies, however, remember that isn't the vacancy that's hops, it's the silver ion pushes its way through over here, the vacancy moves here, the silver ion has to push its way through here, and vacancy over here. The silver ion it's harder to do this, so that the mobility of the vacancies is less than the mobility of the silver ions, of the interstitials. Okay, so what we get is the following. We will get an equilibrium. The concentration of the interstitials and of the vacancies is approximately constant. The concentration of the vacancies is equal to the concentration of cadmium bromide. Okay, this is a divalent salt, cadmium bromide, same thing before. The bromines, you put one cadmium bromide, it replaces two silver bromides, so you get a cadmium on the site, and here you get a vacancy. Okay, so every time, well, you got a cation vacancy. Okay, so every time you put a cadmium on the interstitial site, every time you add a cadmium bromide, replaces two silver bromides, you get a vacancy. So this is called an extrinsic defect. If you have pure silver bromide, you'll have a certain concentration of interstitials and a certain concentration of vacancies. This is called the intrinsic concentration. It's just in pure silver bromide by thermal activation. Silvers now and then pop off the lattice site, go into here, and then move through. So this is your intrinsic concentration. When you're adding cadmium bromide, this is a doping. You're doping it with cadmium bromide, and every time you add a cadmium bromide, you're forcing a vacancy to be formed. So this is an extrinsic defect. Okay, it's being added. Okay, it's not given by thermal activation, it's simply given by the fact that the concentration of cadmium bromide, the concentration of vacancies, is approximately equal to the concentration of cadmium bromide. If the concentration of cadmium bromide, the concentration of cadmium bromide is much larger than the intrinsic concentration of the vacancies, then the number of intrinsic vacancies is much greater than the number of the extrinsic vacancies, and the number of vacancies is pretty well determined by the mole fraction of cadmium bromide. Okay. The product, however, is still constant, because the product is basically still the product of the two concentrations is still the probability that the two are going to find each other. So if you increase the concentrations of vacancies, there are more vacancies for the silver interstitials to fall into, if you like. So you increase this concentration, you're going to lower this concentration. Okay, the product's staying the same. Okay, so the concentration of the silver ions then is equal to the K divided by the mole fraction of cadmium bromide. So as you increase the concentration of extrinsic defects, cadmium bromide, you decrease the concentration of silver. Okay, this is sigma is the conductivity, the electrical conductivity times the charge of an electron. And as I said, the conductivity depends upon two things. It depends upon the concentration of the charge carrier and its mobility. So the concentration of the charged electronic is equal to the concentration of silver ions times their mobility plus the concentration of vacancies times their mobility. Okay, so what's happening now then? Okay, so this is the intrinsic composition. So let's just, okay, is that clear what's going on now? Okay, I'm adding cadmium, I'm assuming that I've added enough cadmium bromide that the extrinsic vacancy concentration is much higher now than the intrinsic. Okay, so the number of vacancies is pretty much equal to the mole fraction of cadmium bromide. Silver interstitials are decreased by the number of calcium bromide. The total conductivity is the concentration of each type of charge carrier times its mobility. So you write this out. I'm going to take d sigma dx. Remember I said now you have a minimum here. We had a minimum where we had this was the conductivity and this was the mole fraction of cadmium bromide, and it went through some sort of a minimum. Okay, so if I take d sigma dx, set it equal to 0 in order to find the minimum, I end up with a minimum concentration, which is equal to constant times the product of the mobilities. Okay, so the minimum is equal to K. That's fine, but what's happening now? Why is there, okay, so you can work it out, you just do the mathematics and you find there's a minimum. If you just work it out, you find it really does go this way. But what's happening is the following, is that the mobility of the silver interstitials is quite a bit larger than the mobility of the vacancies, just because it's harder for these things to push themselves through. Okay, so what's happening then, at first, this is the major thing. In pure silver bromide, the conductivity is mainly by the silver interstitials. The vacancies don't move very much because they're so immobile. Okay, there's only in pure silver bromide, there's very little conductivity by the vacancies. It's mostly covered by this. So as you start to add the cadmium bromide, you're lowering the silver interstitial concentration is lowering because they're all falling back into the vacancies. So you're lowering the concentration of the silver ion, interstitial silvers, and the conductivity decreases. But if you add enough vacancies, now you've got so many vacancies that this term here starts, the vacancy conductivity starts to become important simply because you have a whole lot of them. And so it starts to go back up again. And this is quite observable. Clear? And this is this is called extrinsic, these are intrinsic. The vacancies in pure silver bromide are intrinsic vacancies, which are caused only by thermal excitation. A silver ion simply popping out of its lattice site, forming a vacancy in an interstitial. The extrinsic concentration is given by actually adding a dopant, and every time you add the dopant, you just introduce the thing here. Okay, and then this is completely analogous to your semiconductors. If you know your semiconductor theory, you would have here your conduction band, and let's see, down here is your valence band with the gap energy in here, and this is full. Let's say you're taking pure silicon. You can have intrinsic conduction, that is an electron from the valence band pops up into the conduction band, and now you get an electron here and you get a hole down here, and the concentration of the electrons times the concentration of the holes is equal to a constant. That's your intrinsic conduction in, say, silicon or germanium. Now you add something that's more that's an element of group 4. You add an element of group, what do we do now? We add an element of group 5, like arsenic, which has an additional electron. Okay, so the element group 5, you could put, they write it like this, these are the arsenics. And an arsenic can very easily lose its electron. It's got, put an arsenic into the silica lattice, it should have a valence of 4, it's got an extra electron on it, it's easy to get rid of it. That forms up here, this forms an electron. So every arsenic that you add basically gives you an electron, because this is such a small activation energy here. Almost all the arsenics that you add lose their electrons, which then move through the conduction band. Okay, so that's adding an extrinsic defect. And if you add enough arsenic, it's the same thing as here, simply the conductivity then simply becomes equal to the concentration of the arsenic. Meantime, you're increasing, by adding the arsenic, you're increasing the electron concentration, and you're decreasing the hole concentration, because you got a whole lot of electrons, they can fall into the holes. The intrinsic conductivity is thermally activated. That is, the intrinsic conductivity varies as the logarithm, as log conductivity varies as 1 over T, because there's an equilibrium constant. So any thermally activated process, the log of the concentration varies as 1 over T. The concentration is exponent of minus delta G over RT. Here is equal to the exponent of energy of a gap over RT. So it's thermally activated, so it goes up very, very rapidly as you increase the temperature. The extrinsic conductivity, of course, doesn't, because it's not thermally activated. It just depends upon the amount of dopant you add. In fact, it goes the other way, because once you get into this regime over here, where the vacancies are controlling the whole thing, the concentration of vacancies is constant. It's simply equal to the mole fraction of cadmium bromide, and the mobility can actually, in certain cases, decrease a bit with temperature, or certainly doesn't increase that much. Okay. That's all I want to say about defects. Any questions about defects? All right. I want to. Go back to the change of pace. Go back to the compound energy formalism. Two sublattice compound energy formalism. I'll be talking about it in the Bragg-Williams. I won't be talking about quasi-chemical model, the two sublattice formalism for compound energy formalism. We've applied the compound energy formalism to say things like molten salts, where the end members are actually real components, like sodium chloride, potassium bromide. We've applied the compound energy formalism to things where the end members are hypothetical things, like this would be, this is AB, and over here you've got A vacancy, and this is vacancy B, even though you really only. Okay, so these are all hypothetical compounds, but they're still, so they're totally hypothetical compounds, but they're still neutral things. They're not electrically charged. Now we can go to take the formalism even further, where these compounds, some of these end members over here, can be so hypothetical that they're actually a compound which has a net charge on the compound, which is obviously not something that's possible. But it certainly simplifies things. So I'm going to go back to this number 1, which is this old chapter I wrote many years ago, 2001, it's not that long ago. Go to page 64. We're going to consider a model for solutions of, I'll start off with a somewhat simple one, solutions of FeTiO3 and Ti2O3. FeTiO3 is ilmenite, famous ore in Quebec, and Ti2O3 is soluble with it. Okay, so it's a solution of FeTiO3 and Ti2O3.
I'm going to go to page 65.
Okay, the model that we're going to use for this is the following. FeTiO3, that's titanium 4 plus. So 2 plus iron, 4 plus titanium. So that's 6 positive charges, 6 negative charges. Ti2, so FeTiO3 is Fe2 plus, Ti4 plus O3, where you have 2 sublattices. The iron's on one sublattice, the titanium's on another sublattice. Ti2O3 is Ti3 plus 2 O3, or actually it's actually better to write it this way, Ti3 plus O3. The 2 titaniums could be considered to be on 2 separate sublattices. So when you make a solution of the two, the iron and the Ti3 plus can mix on that site, and Ti4 pluses and Ti3 pluses can mix on the other site. The oxygens stay constant, so there's a third oxygen sublattice, but we don't have to worry about it. So we can do the compound energy formalism like this then. Down here we have Fe2 plus Ti4 plus on our two sublattices. I want to add O3 to that. So this corner down here is stoichiometric ilmenite FeTiO3. Over here, now we're going to model this as follows. We're going to model it as Fe2 plus Ti3 plus, Ti4 plus, Ti3 plus, O3. So in this sublattice you can get iron and titanium 3, and in this sublattice you can get titanium 4 and titanium 3. So doing it that way then, we have our 4 compound. That one compound is iron titanium 4, the next compound is iron 3. Every pair of atoms in the 2 sites gives you an N member. So over here then, we're just continuing through the formalism. Over here you have Fe2 plus, Ti3 plus, O. Okay, and that has a net negative charge. Okay, this is 2 plus 3 is 5 pluses, O3, so you've got 6 negative oxygens. So this is a charged compound, which of course is obviously totally hypothetical. Okay, so this is FeTiO3 minus. Up here you have another pair, which is Ti3 plus, Ti4 plus, O3, and that has a net positive charge. 7 positive charges, 6 negative charges. And over here then you have Ti3 plus, Ti3 plus, O3, and that one happens to be neutral. Okay, so in this system then, you obviously cannot have a total solution which has a net charge. So this is your neutral line. So all real solutions must lie on the neutral line. You can't actually have any solution that's off here. This is the line in which the total number of electrons is 0 in the system. I'm going to call the site fraction here little x. I'm going to call the site fraction here little y. Okay, and we're going to write the compound energy formalism. So the Gibbs energy of the system is going to be 1 minus x times, okay, and along the neutral line, x equals y. Well, let's do it this way. 1 minus x times 1 minus y times g naught. Let's call these so that I don't have to write it out anymore all the time, let's call that compound 1. This is N number 2. This is N number 3. And this will be N number 4. Okay. Times G naught of 1 plus x times 1 minus y of G naught of 3 plus 1 minus x times y of G naught of 2 plus xy times G naught of 4 plus RT x log x plus 1 minus x log 1 minus x plus y log y plus 1 minus y log 1 minus y. It's compound energy formalism. I won't even put in the short range order term. This is just your standard. And along the neutral line, you can put in x equals y. That simply keeps the total charge equal to 0. We're going to have delta G of exchange is going to be G naught. How did I do that? G naught 2 plus G naught 3 minus G naught 1 minus G naught 4. That's your exchange reaction as you normally get in a reciprocal system. It's for the reaction of this plus this. This plus this forms this plus this. Your exchange reaction is always this diagonal. This plus this gives you this plus this is your exchange reaction. And that's your exchange Gibbs energy. Okay, well those are the Gibbs energies. So the only Gibbs energy here, well, the Gibbs, so G naught of 1 is the Gibbs energy of ilmenite. G naught 4 is the Gibbs energy of Ti2O3. G naught 2 and G naught 3 are completely hypothetical things, but they have to do with the exchange of sites. Okay, so if we then do all the substitution, and I'll let you play with this yourself, x equals to y, the exchange Gibbs energy is equal to this. Okay, what you're going to get if you make the substitutions, and I'll let you make the substitutions yourself and play with it. When you simplify that down, it's very simple. When you simplify that down, making the substitution x equals y, and this making the substitution for delta G exchange, put it back into that expression. That whole thing simplifies to Gibbs energy of the solution is x times G naught of Ti2O3 plus 1 minus x times G naught of FeTiO3. Just the real materials. These are the Gibbs energies of the real materials. Plus x times 1 minus x times delta G of exchange. So what have we come up with? We've come up with basically what's like a regular solution. It's a regular solution between Ti2O3 and FeTiO3. Sorry, we got to add on these. Plus the 2RT x log x plus mixing term as well. Okay, there's a mixing term for it. So this is your ideal mixing. So it's basically a regular solution, although you're mixing two sublattices. You're mixing titanium. Going back to this, it's Fe2 plus, Ti3 plus, Ti4 plus, Ti3 plus O3. Here, an ideal mixing term is simply an ideal mixing of iron and titanium 4 plus on one site and titanium 3 plus, sorry, Fe2 plus and titanium 3 plus mixed randomly on one site, Ti4 plus and Ti3 plus mixed randomly on the other site. So you got your random mixing term with a 2 here. This is just your x1 g01 plus x2 g02. And then you have a term here which is like a regular solution term, x times 1 minus x times delta g of x change, where x is simply the mole fraction of Ti2O3 in the binary system along the joint. Now you see this, that these two parameters here, if you want g, you need to know the Gibbs energy of the pure materials, okay, because that's your endpoint, Gibbs energies. But here you have only delta G exchange. You don't actually need the individual Gibbs energies of these two charged, G2 and G3 were the two charged compounds. Okay, all you need is the difference here. Okay, all you need is the difference. You don't actually need the Gibbs energies of the pure compounds. You could choose one of these arbitrarily, and the other one would give you delta G exchange. So G2, remember G2 and G3 were the two charged compounds. Okay, you make G2 equal to whatever you want, 0, and then G3 is given by delta G exchange plus G1 plus G4, or any way you want to do it. There's only one real parameter. One of these is necessarily arbitrary. Only the sum. Only all that's necessary is that the sum of these two equal the sum. The sum of these two has to be the same. Oh, sorry, yeah. The net charge here has to be 0. You make one anything you want, but the other one is how you want to do it. And x is equal to y. So this is your model parameter. Your model parameter is this. Then you have the formalism parameters. G2 and G3 are formalism parameters, but the real model parameter, the only thing, is delta G exchange. As long for any sum G2 plus G3 equals constant, it doesn't matter what the individual values are, you're still going to get exactly the same. Okay, you could let G2 be 5 and G3 be 10, or G2 be 10 and G3 be 5. You're going to get the same delta G exchange. You're going to get the same G. Now the way that FactSage sets the x equals y is what you actually do in FactSage is you enter the compound, you enter the n member as a charged compound. Okay, I enter my n members, I enter them as, well, FeTO3 neutral, Ti2O3 neutral. I enter it as TiO4, this other corner up here, which was positively charged, as plus, and this one down here was the FeTiO3 minus. I enter that as actually FeTiO3 minus. The minus becomes the electrical charge becomes another component, if you like. So I say my n members, I tell it, FactSage, that this is a charged n member with one positive charge. I tell it that this is a charged n member with one negative charge. That these two are neutral n members. Okay, in FactSage, and the total number of electrons, the total charge, is equal to 0. Okay, so then it simply it simply solves along this line. It doesn't know from neutrality, but you're telling it the electron, if you like, the electron is an additional component, and this n member contains 1 electron, and this component contains minus 1 electrons. And the total number of electrons in your whole thing when you enter your reactants is 0. So the total number of electrons is 0. This has 1 electron, this has minus 1 electron, so this always has to be equal to, the sum has to be equal to 0. So it automatically just makes sure that okay. But when you look at the mathematics, that's basically what it's doing here. Okay, now why do we do this? Why introduce all these charged compounds and all this? Well, because we can then model these ceramic materials in terms of exactly the same algorithm, exactly the same formalism we use for everything else. We don't have to do any new programming. It's still the same compound energy formalism as we use for molten salts, as we use for defects, as we use for vacancies, interstitials. It's exactly the same formalism. You enter the Gibbs energy of the n members, you enter their stoichiometry, including their charge. Be sure you understand the difference between a formalism parameter and a model parameter. And away you go. Same algorithm, you don't have to add a different. Okay, let's look at this a little differently now in terms of what is why is this the model parameter? What is this delta G exchange? What's it mean exactly? How does it work out this way? Let's look at it as if we did not have, before we had the compound energy formalism, actually which came around about 1990. Everybody was kind of hinting at it, but then Matt Sillard, I actually happened to be at the talk that he gave, where he talked about the compound energy formalism and how you could apply it to ionic compounds, and most people in the audience didn't quite know what he was talking about, and everybody kind of said he's crazy. I mean, charged compounds and so on. But a few people who had been struggling with this, like us, said this was a revelation. This is one of the major things, I think, that ramped CalFET up a couple of levels, was the compound energy formalism, when suddenly you realize that all of these things could be put into one sort of formal algorithm. Okay, but say before 1990, how would we have treated this ilmenite Ti2O3, which is a very important solution, and that's what ilmenite ore is. It's ilmenite, but it's got a bunch of Ti2O3 in it as well. How would we have treated this before? And this was back, so here on page 65 of the handout number 1, I talk about, this is what I just did. Go back page. Actually, this was 2001, so people were still thinking the old way, so I did it an opposite direction now. So let's say, so here's your, okay, so up here now we have, this is the solution I just talked about. Iron 2+, titanium 3+ on the A lattice, titanium 4, titanium 3 on the B lattice. So I know the iron and the Ti4, they're mixing, these are mixing on their lattice, these are mixing on these lattice. So this is your random mixing term, so fine, there's your random mixing term there, same as before. Or X. X is the distance along here, Y is the distance along here, but X equals Y along this line, so X is really just the mole fraction as you go from ilmenite FeTiO3 to Ti2O3. X is just the distance along. It's a binary system, if you like. And what we said then was it's a pair, this is Fe2+, these are pairs on opposite sublattices. So you consider your two sublattices. This is one sublattice here, and this is your other sublattice here. We have a pair of atoms here, plus a pair, these pair form, the exchange reaction is actually the change in your nearest neighbor pairs. It's a pair of iron 2+, okay, let's put it here, iron 2+ on the A site, and titanium 3+ on the B site, so that pair between iron 2+ on the A and titanium on the B site, plus titanium 3 and titanium B on the B site, gives you a pair exchange. It's the exchange of nearest neighbors. You have this nearest neighbor pair, iron 2+, titanium 4+, titanium 3, titanium 3. There's a flip, and you form this nearest neighbor pair. And that, the delta G of that reaction is the exchange reaction gives energy. And the probability of finding this pair is X. The probability that an AB pair is an iron 2+, 3+, or a Ti3+ is equal to X times 1 minus X. Okay, the probability of the X, the probability of the... You see how it gets complicated when you don't use the compound energy formula. The composition of this is 1 minus X, X. This is 1 minus XX, because every titanium 2+ is going one thing here and one thing here. When you take FeTiO3 and you add Ti2O3, you're adding one titanium 3+ to this lattice and one to this lattice, so it's 1 minus XX, 1 minus XX. Okay, the probability of a 2+, 4+ nearest neighbor pair is 1 minus X squared. The probability of a 3+, 3+ pair is X squared. The probability of a 2+, 3+ pair this way is X times 1 minus X, and so on. You work the thing out. The probability that an AB pair is either this kind of pair or this kind of pair is equal to X1 minus X. And when you put the whole thing back in, you find that you get an excess Gibbs energy, which is equal to X times 1 minus X times A plus BT. But the A plus BT is the delta G exchange, so you're back to exactly the same. But here you've had to use an actual model for this particular material. You had to know that one. Okay, so you could write a separate model for ilmenite Ti2O3 mixtures. Think about what you do. But this shows you why the exchange gives energy as the model energy. It's really the change in first nearest neighbors. It's really determining the whole thing. Okay, so this is the you see then that your real model equation is delta G. Here we don't have to talk about charged compounds. This is like a real model, not using a formalism. We're mixing this stuff up, we're thinking of how the nearest neighbors fit, with the energies of the near neighbor, we're the whole thing out, we end up with the same equation as we did by doing the thing, shoving the whole thing into the compound energy formalism. In the compound energy formalism, you have to talk about these charged compounds, but you see, it's just a formalism. You don't actually have charged compounds. That's why it's called the compound energy formalism. You're treating things as compounds that aren't really compounds, but the differences are actually real model parameters. Okay, are there any questions about that thing? Okay, because now I'm going to go on to probably can do this in 10 minutes. All right, let's go on to some more complicated ceramics now. Okay, so when you get to ceramic compounds, like the ilmenite thing, then the compound energy formalism really becomes useful. Okay, so let's talk about a spinel. You know what a spinel is? Okay, Spinel actually, the Spinel is actually MgAl. Just to make it clear, MgAl2O4 is a mineral called Spinel. Okay, and it has a certain crystal structure, but Spinel is also now the name of any material that has the crystal structure of Spinel. It's called a Spinel. Okay, and the Spinel, basically, this is a 2,3 Spinel, so you have the aluminum, the magnesium is 2+, the aluminum is 3+. You have two different cationic sites. These cationic sites here are tetrahedrally coordinated, that is, they have 4 oxygens around them. Okay, so this magnesium finds itself surrounded by 4 oxygen ions in the form of a tetrahedron. And these aluminum 3+2, these are called octahedral sites, and they're surrounded by 6 oxygen ions at the corners of an octahedron. Okay, the oxygen sites form an almost, the oxygen ions form an almost face-centered cubic array, not quite. Okay, so you can imagine a face-centered cube of oxygen ions at the corners and oxygen ions at the centers of the faces. And then you know in a face-centered cube you have octahedral sites like the very center of the cube. If you take your cube at the corners of the cube and in the centers of the faces, you have oxygen ions, then you have octahedral sites in the center of a face. The center of a side here is an octahedral site if you consider the neighboring ions. The neighboring unit cells, this site here has six oxygens around it. So this site here would have 1, 2, 3, 4, 5, 6 oxygens at the corners of an octahedron around it. And somewhere around the corners of this cube you have 8 sites at which you can put a tetrahedral, which are tetrahedrally coordinated, and so on. Okay, anyway, so you have certain tetrahedral sites where you can put the cations, and you have certain octahedral sites where you put the cations. In the Spinel structure you don't fill all the sites because when you have, in the unit cell you have four lattice sites. So the unit cell, this unit cell with the oxygen at the corners and the oxygen at the centers of the faces, all the lattice sites, the oxygen sites are all filled. You have, in a cubic face-centered, you have four octahedral sites, but only 2 are occupied by the aluminum, the other 2 are vacant. But these are not randomly, there's special octahedral sites, 2 octahedral sites here, then the next lattice is this way. So it really is the sublattice has 2, you don't have to worry about this, it has 2 oxygen ions. There are 8 tetrahedral sites in the face-centered lattice, only one of them forms this sublattice. So you have one sublattice which is formed by 1/8 of the tetrahedral sites, but a very specific way of choosing the 1/8. You have octahedral sites which are 1/2 of the octahedral vacancies in the lattice, then you have the O4. You don't have to worry about the exact structure, but this is what they mean talking about the tetrahedral and the octahedral sites. There are basically three sublattices, an almost face-centered cubic oxygen ions. There's a sublattice of tetrahedral sites, which contains one site for every 4 oxygens, and there's a sublattice of octahedral sites, which contains 2 lattice sites for every 4 oxygens. Okay, so if you have Mg2 plus Al3 plus 2O4, then all the tetrahedral sites are occupied by magnesium, all the octahedral sites are occupied by the 3 plus ions, and that is called a normal spinel. The normal spinel is of the form A2 plus, B3 plus 2, O4, that's called a normal 2,3 spinel. You then have what we can call an inverse spinel. Now magnesium, MgAl2O4 is pretty much 99% normal. An inverse spinel is B3 plus, A2 plus, B3 plus 2O4. In an inverse spinel, all the tetrahedral sites are occupied by half of the B3 pluses. An inverse spinel still has the overall stoichiometry AB2O4. It's A2 plus, B3 plus 2O4. But the 3 pluses prefer the tetrahedral sites. The A2 pluses prefer the octahedral sites. The remaining B3 pluses also go on the octahedral sites, and these kind of mix randomly on the octahedral sites. So that's called an inverse spinel, and certain spinels are inverse. It all depends upon really the electronic orbital structure. Certain ions form better bonds when they're surrounded by 4 oxygens because of the symmetry of the orbitals. Others form nicer bonds when they're surrounded by 6 oxygens because of the symmetry of the orbital. The overlap of the orbitals is higher when you've got 6 than when you've got 4. So in MgAl3O4, obviously the magnesium prefers the tetrahedral sites, the aluminum prefers the octahedral sites, and this one, the B's prefer this. So there's a site. Basically you have A2 plus on the A sites plus B, 3 plus on the B sites forms A2 plus on the B sites plus B, 3 plus on the A sites. You have an energy like that, that's called the site exchange reaction. If this site exchange reaction has a certain Gibbs energy, if the Gibbs energy is very negative, if the Gibbs energy is very positive, then you get a normal spinel with the A's on these sites and the B's on the B sites, if delta G is positive. If delta G is very negative, then you prefer, the A's prefer to be on the B sites and the B's prefer to be on the D sites. Okay, so this is called the delta G of the site. This is the site inversion. Or the site exchange energy. Okay, site exchange energy is positive, you get a normal spinel. Site inversion or site exchange energy is negative, you get a inverse spinel. And you can also, if for values that are not minus or plus infinity, you get a mixed spinel. And a mixed spinel has A2 plus, B3 plus, A2 plus, B3 plus. That's a mixed spinel, in which you have A pluses and A's and B's in the 2 sublattices. Okay, the principle. Okay, so it's kind of, is it clear now? You have 3 sublattices in the ratios with site ratios in the 1, 2, 4. We can forget the oxygen because it's always occupied. So we have 1 tetrahedral site and 2. The ratios of the tetrahedral and the octahedral sites are 1 to 2. You can have inverse spinel, mixed spinel, or inverse spinel, normal spinel, inverse spinel, mixed spinel, depending on what A and B are, what elements they are. Okay, MgAl2O4 is mainly normal, Fe2 plus, Fe3 plus O4 is mainly inverse. That's magnetite and so on. And the principal, there are others, but the principal model parameter is basically simply the site inversion energy. the A's 2 pluses and the B 3 pluses, their relative preference for the tetrahedral and the octahedral coordination. That's your main thing, but of course other things enter into it as well. Spinels are extremely common, they're ubiquitous. Just about any ions, aluminum, magnesium, calcium, zinc, lead, so on, could go into these. If you look at the fact stage model, we have like about 30 ions on each of these sites. And many of them are mixed, normal, inverse, and whatever. The properties of spinels, the magnetic and electronic properties, can be greatly influenced by the say if A plus or B's are, any of these are iron, for example, then, you know, like an iron metal, you have a ferromagnetic material. When the irons are next to each other, they tend to line up and form ferromagnetic material. If you have certain ions, if you have iron ions in these sites, depending on the relative concentrations of these things, you can have a ferromagnetic material in which they tend to line up. You can have an anti-ferromagnetic material in which they tend to oppose each other. And you can control the magnetic properties by adding other things like magnesium and zinc and so on, which change the site. And if you put all the irons on the same site, you get a different magnetic properties than if you put the iron on the two sites. You can force the irons to go on this site, however, by putting, if you want to force all the irons to go over on this site, then you put in something else that strongly prefers the tetrahedral sites and shoves all the iron back to those sites. Okay, you can also affect the electronic conductivity, because these things are electronic conductors. You can do it by hopping, and they can hop more easily between lattices than among sites on the same lattice, so you're affecting electronic conductivity. So you can, by doping these things and playing around with the elements that are in there, you can affect the electronic and magnetic properties and come up with what's called functional ceramics. Okay, and they're just very ubiquitous compounds that are all over the place in our skull around. So how are we going to model these spinel? This, by the way, is strictly speaking a 2-3 spinel, meaning you have 2 plus and 3 plus ions in it. There are other spinels, or 1-4 spinels and so on, which I won't go into, but you can also have 1 and 4. It's kind of a similar thing. But the main spinels we deal with are the 2-3 spinels. So those are the that's the spinel structure. Okay, just to show you how life was, if you can just listen here. 5 minutes. How life was before we had the obviously I think you can see how the compound energy formalism is going to be applied to this. But before we had the compound energy formalism, what did we do? I did this in 1971, way before the compound energy formalism. Got some papers on it too. Here, this is handout number 33. You don't have to know handout number 33 because this goes back to, actually this was 1993. So actually we're just starting the compound energy formalism, but we'd already done this thing and I'd already written some papers back in the 70s on it. How would we model the system cobalt, iron, manganese, spinels, cobalt, iron, manganese, oxygen? Now all of these, cobalt, iron, and manganese, all have 2 plus and 3 plus ions, which are, both of which are important. You can't assume, like calcium, that you only have one valence state. How would we model the cobalt, iron, manganese spinels? You don't have to read all this because there's a whole bunch of stuff here that doesn't matter. That's not the point of the paper. You don't have to also know the paper either. Where did I write this? All right, here we go. This would be the model. So we have 2 sublattices. This is your tetrahedral sublattice with 1 site. This is your octahedral sublattice with 2 sites. All right. Cobalt 2 plus and 3 plus, iron 2, 3, manganese 2, 3 can go on all sites. And in order to model this thing, we have to somehow have energetic parameters that will permit us, model parameters that will permit us to calculate all 12 compositions. Okay, so we have cobalt, these are little A, B, C, D, E, F, G, H, I, J, K, L are the stoichiometric factors. Okay, so no compound energy formalism, we're trying to think what's really going on here. Okay, so A plus B plus C plus D plus E plus F has to equal 1 because there's total 1 tetrahedral site.
and G plus through I through L has to equal 2 because there are 2 octahedral sites. So you do have this thing. Then you have the charge balance, has to be neutral. So 2 times the concentration of all the divalent elements, 2 plus, this is 2 plus, this is 2 plus. So this is 2 times the concentration of all the 2 pluses, plus 3 times the concentration of all the 3 pluses, has to equal 8 because you have 4 oxygen ions. And then we have the overall, we can't really put ourselves anywhere in here because we're really in a ternary system. We're really mixing Mn3O4, CO3O4, and Fe3O4. So we would have the total amount of manganese is equal to 1 minus X minus Y. Okay, where X manganese oxide and X cobalt oxide are the overall mole fractions. So you really have a ternary system. It's really Fe3O4, Mn3O4, and CO3O4. Okay, so you really have 2 mole fractions here. So those 2 mole fractions then are really determining the sum of these things. Now then, we have to consider all the equilibria between them. So here we have a site exchange reaction like this between the iron 2 plus and the iron 3 pluses. Okay, so this is one site exchange reaction. So the delta G of that site exchange reaction, which is a model parameter, is minus RT log of the concentrations of this times this over this times this. Then we have a site exchange reaction for the manganese, 2 plus and 3 plus, and the delta G of that's minus RT log of the concentrations of these over these, so that's 4 more. Okay, and we have one between, now that's between iron and manganese. We have a site exchange between iron 2 and manganese 3, and we have a site exchange between cobalt 2 and cobalt 3. The other ones between iron and cobalt and iron and so on are not independent parameters because they're given by the differences of these. So we have the 4 independent site exchange reactions. And we also, if you think about it, we actually end up having exchange equilibria 22 and 23 are redox reactions. So we have iron B, 2 plus, manganese B, all on the B sites. So these are all on the same sites, but this is iron 2 and manganese 2, and the B sites form iron 2 and manganese, iron 2 and manganese 3 on the B sites form iron B and manganese, iron 2 and manganese 3 on the B sites. So you got a redox reaction on the A sites, you have a redox reaction on the B sites. When you go through the whole thing, you find that these are the only independent reaction equilibria you got. Okay, so now you have 12 unknowns, and you have 12 equations to solve. Okay. So you take your 12 unknowns, you have A, B, C, D, F, G up to L, you have 4 sort of mass balance equations, charge balance, mass balance, and just overall moles. You take an overall mole fraction of the system in terms of manganese, cobalt, and iron. So for any overall composition of the system, you have 1, 2, 3, 4, look at this, 5, 1, 2, 3, 4, 5 linear equations, but then I think you end up with 7 equilibria. Okay, 5 of which are site exchange, site inversion reactions, and 2 of which are redox reactions. So we have, these are your 7 model equations. 7 model parameters are the delta G's. Then you have these 7 plus 5 equations to solve simultaneously in order to get to all your things, and then you can put them all back in. You can calculate the Gibbs energy with it. That's how you had to do this thing before we had the compound energy formula. And I actually wrote a program that did this back in the 1970s, and it worked. And I can even show you the references back to these papers if you want. So that's to give you an idea of how important, and that was only for the 2,3 spinels. Now, if you then had a 1,4 spinel, there's all sorts of ceramic compounds that are similar. You have 2 cation lattices. You have olivines, you have all sorts of things, melanines, all sorts of different things that are different structures, but basically it's the same sort of idea. You have 2 sublattices, sometimes 3, but basically you have 2 cation sublattices which things exchange, and you have exchange reaction. Okay, so you got these are all your model parameters. There's nothing in this that talks about charged compounds. This is straight model. Okay, but now anyway, my point was this is the model for 2,3 spinels, and you can see really anything more than iron, cobalt, and manganese. If you wanted to add any other elements, then you're totally lost. A 3 metal model was the end. What you could do here.
and trying to solve this thing. So to try to build up a big database like in FactSage with 10 different metals would be... In any case, if you wanted any other ceramic that had two sublattices but with different ratios and so on, then you'd have to write an entirely different model. So we'd have to have, for every type of ceramic, your olivines, your perovskites, and so on, every one would have to have a separate model. The point is, which I will show you tomorrow then, is that we can take this whole Spinel thing, we can put it into the compound energy formalism, which is already programmed. Okay, then you're going to see that the formalism parameters reduced back to these model parameters. And so that's how we build up the database using the compound energy formulas. The important thing, which is not easy, is to try to, when I get to that, is to try to separate your formalism parameters from your model parameters. Even in the example I gave of the ilmenite a little while ago, you can see that you have to be careful as to what really are your model and your formalism parameters, and this can become more complicated with the Spinels. But Sergei Dektorov wrote a good paper once in which he really identified what are the model and formalism parameters. You can't just randomly set things to be zero and like, it's kind of equivalent to that Vacansonian vacancy, well the G is zero. No, it isn't. You have to think about what you're really talking about. But this whole compound energy, you can see now why the compound energy formalism basically revolutionized the whole idea of what we're doing in CalFat, because there's no way you could build a database for all different kinds of ceramics with 10 different elements in it if you didn't have some sort of a formalism that you could put everything into. You'd have to be doing this kind of thing constantly. All right, so I'll talk about that. You don't have to read this paper, I'm just trying to show you what to do. But for coming tomorrow, you might want to look at handout number, what do we call it? Number 23. And that'll be going on talking about slags. I added a new one, number 49, so 23 and 49 are the ones I'll be talking about. Let's see.